Okay, welcome to the particle diagram activity on Schoology. What we're going to need you to do is get a piece of paper, put your name on it, and write particle diagram activity. So if you need to pause the video in order to get that all situated, go for it. A little while ago, we did an activity, if you were in class that day, where we compared elements inside little glass vials to the compounds that they create when they form ions or form bonds with each other. And we made particle diagrams for sodium, iodine, and sodium iodide in small groups. And then what we've done as your teachers is we've taken some examples of the particle diagrams that were produced by students, and we have put them into this activity to help sort of learn and see where everybody's minds were when they were drawing these particle diagrams, and hopefully pick what we can come to a consensus on as the best diagram for our submicroscopic or particle area of this Johnstone's triangle. So the sodium metal didn't quite look like this, probably wasn't nice, perfect, round little pieces, but very shiny. It's a soft metal, so you can cut that with a butter knife, and this is just a picture I pulled off the internet. Symbolically, this is sodium. So Na is the symbol for sodium, and the S in parentheses is representing the physical state of sodium. So in this case, it's a solid because it's a metal up here. Okay, so solid. Then the particle diagram was the piece that we really wanted you guys to get at. So we're going to look at some examples of particle diagrams that students have drawn. And this is going to be the first part that you're going to write on your paper. So we're going to look at each of these particle diagrams, and I want you to do this for each one. For each particle diagram below, address the following. A, what is correct about the diagram? B, what is wrong or incorrect about the diagram? And then 2, which diagram do you think is the best representation of sodium at that submicroscopic level, that particle level? Explain why you think so, and explain how it could be improved further. So go ahead and pause the video and take a minute or two to do this for A, B, C, and D below. So you're going to write what's correct, what's incorrect about each of the 4 diagrams, and then number 2, identify which one is the best in your opinion, explain why you think so, and explain how it could be improved further. So go ahead and pause now. Okay, now we're going to go through that same process for iodine. Okay, up here, we had a vial of little tiny pieces of iodine. When you roll that vial and those roll around each other, they look a little bit less black. They kind of look like a navy blue or a really dark purple, depending on your perception of the electromagnetic spectrum. Okay, symbolically over here, iodine, I-N-E, it's a halogen, and the gens, or the enes, they are always diatomic. So they exist in pairs of themselves. That's why we have the 2 here. So I2. And again, it's a solid, so we put the little S in parentheses. Submicroscopic level, that was the piece that we were really focusing on you guys drawing. And on the next slide, we're going to have an example or set of examples of what people came up with for that particle level diagram. So same process. What we want you to do, pause the video. For each of the pictures, A through F, write what is correct, what is incorrect, and then number 2, write which one you think is the best, explain why, and explain how it could be improved further. Pause the video now. All right, third one. When we put sodium and iodine together, we're going to end up with an ionic compound called sodium iodide. Sodium iodide looks a lot like table salt, and in fact it is a part of our table salt because we need iodine in our diet. So we have iodized table salt. A little portion of it is sodium iodide. So that's what it looks like at the macroscopic level. Symbolically, sodium becomes a +1 ion, iodine becomes a -1 ion. Those balance each other. So NaI is our formula. And again, S in parentheses to indicate that it's a solid. Okay, we talked a lot about the properties of sodium and iodine changing dramatically when they become sodium iodide. We went from a shiny silver metal that's soft and a black or blue or purple solid that's kind of sparkly to this white crystalline substance when they combine. Okay, now submicroscopic, what do you think those particles look like? And we got a variety. We got a much bigger variety. So you're going to do a little more work for sodium iodide. Okay, so A here, B, I think they were looking at maybe drawing two of those salt crystals, those NaI crystals, and then kind of what they would look like inside. And then, a variety of different examples here. So pause the video, write what's wrong, what's correct about each diagram, and then number 2, which one do you think best represents the sodium iodide? Okay, now we're going to look at how you did. So again, we've got our macroscopic level, our symbolic level, and then the third part of the triangle would be the particle diagram. And when we look at a computer diagram, this is what that particle diagram looks like. We end up with an organized pattern of atoms. Okay, they're all sodiums, so they all look the same. This one is kind of, I think, trying to show the malleability of sodium. Okay, these could slide past each other because of that sea of electrons model that we've been talking about. Okay, but again, organized pattern, all the same. They're all touching because it's a solid. Okay, so if we go back and you look at sodium up at the top, and see which model you picked out of the A, B, C, D models that we were showing you from our student drawings, okay? And we're going to say, I would say B and D are a tie as far as the best model on those pictures, okay? B was drawn a little bit bigger than D, and that's one of the things I liked better about it than D. And we have, again, an organized structure of atoms. They're all touching each other. This top row kind of floated away a little bit, but I think they meant to be all touching. Okay, so that's a great diagram. One of the things I really like about D is the little vibration lines around here. So we're showing that there's still movement among the atoms in a solid. They're just vibrating in place. So I really like that. So either one of those would have been a good choice for sodium. All right, so if you got those right, just put a little star next to your choice. If you got it wrong, maybe go ahead and just put an X and then write down B or D as a correct answer. All right, now we're going to look at iodine and see how you did on iodine. So again, our macroscopic level, what you can see with your eyes, our symbolic level, I2, with the little S in parentheses for solid. Again, 2 meaning it's diatomic, it exists in pairs. Okay. If we look at a computer diagram of iodine, what they have here is they have pairs of iodine atoms attached to each other, and then they're all touching each other in our solid. So we're all bonded together in our solid, or at least attracted to each other here. Okay, so they're very close to each other for the solid piece, but it is still showing the pairs, which is a really good piece of this diagram. This is hard to do with a pencil if you haven't seen it before, but if we're looking at those student diagrams, I would say A did a very good job and C did a very good job working on those pairs of atoms that are still attached to each other. So this one is showing those attachments as lines, and this one is just drawing them very close to each other, hopefully simulating that those, again, are in contact, and this is a solid. I would say that picture D, if we were to go back to that slide and look at all of them, picture D had the good vibration lines here. I like that, but I couldn't quite tell if these were individual atoms or if they were pairs of atoms. Some of them look like pairs, but some of them look like individuals, so I wasn't quite sure on that one. If they had all looked like pairs, I definitely would have chosen this one as my favorite of the student diagrams, okay? But if we're looking at the other ones, this one, I love the pairs. Excellent catch on that, but the iodine was solid. We saw that up here. So this is definitely showing a gas form where they're far apart and they have those little whooshies to show that they're moving, okay? Again, here, pairs, but then they're moving a little bit too much. This might be a liquid or a gas, kind of depends on where the group was thinking on that one. Okay, so that one is, that's the reason why that one wouldn't have won. And then this one, excellent diagram of a solid, but it lacks the paired atoms, and so that was lacking for E. But overall, I really liked something about every single picture here. All right, going down to sodium iodide. How did you do on that one? So we have our salt crystals here, NaI, it's a solid, and we're going to look at first a computer diagram. So here's the computer particle diagram. If you look, there's a 1-to-1 ratio of the small purple spheres to the large purple spheres. If you remember back in chapter 6, we talked about trends. Sodium being only in the 3rd row of the periodic table and iodine in the 5th row of the periodic table. If we're thinking about the size of those ions, even if we don't know cation and anion, having 2 extra layers of electrons for iodine is going to make it a lot larger. But in reality, because of the ionic form, it actually has 3 layers more than sodium. When sodium loses its valence electron, it becomes much smaller, only has 2 layers of electrons left. Iodine gains an electron from the sodium, and that completes its 5th layer. So it has 3 full layers more than sodium, and it is much bigger than its atom. So we have these small sodiums attached to large iodines, and I did not expect a lot of students to catch that difference. But I was looking for 1-to-1 ratio, organized pattern, and also, if you notice, we have sodiums are surrounded by iodines. Iodines are surrounded by sodiums because of their opposite charges. I would say the best student diagram was this one. We had a representation of the size difference here, but we also had that 1-to-1 ratio, and they're all touching. This is great. I mean, a little bit of eraser and smudge marks here, but I think this was a really good job. If we go back and we look at all of those diagrams, we can talk about them individually. So A was good as far as showing the size difference, but they're too far apart, and they're existing in little pairs, kind of like a molecule. Remember, ionic compounds don't actually exist as individual units. That formula unit shows a ratio in a crystal, but not something that independently exists. This one, I think the students were thinking, oh, well, iodine is diatomic, so there's 2 atoms, and sodium is monatomic, or not really monatomic, but it exists as single atoms, so when we put them together, we have to keep that ratio. You do not have to keep that ratio. NaI shows the ratio is 1-to-1. If it were NaI2, then we would have a ratio more like this. This one, I'm not seeing any sodium or iodide. I'm seeing one kind of particle only, and we have to have 2 kinds of particles in our picture. This one, again, stuck on that diatomic for iodine, but when you look at the formula for the compound, the 2 goes away. Iodine, in its pure form, is paired with itself, but when it's in a compound, it depends on what it is bonded to for that ratio. Here, I like that we're in a 1-to-1 ratio. However, we lined up all of our positives and all of our negatives together instead of alternating them. So that was a problem here. This one, excellent job of alternating the positives and negatives. And you know what? Honestly, this is what I was expecting the best ones to look like. I did not expect a group to come up with that size difference, and we had several groups come up with that size difference. So I would have said this is great. The only thing that's missing is just something from chapter 6, that size difference. Here, I think they were trying really hard to look like E. D just kind of fudged a little bit right down here where we end up with 2 negatives next to each other and 2 positives next to each other. So keeping it really nice and organized where you definitely have the alternating positives and negatives is going to be a better picture. And then down here, excellent ratio, but this is failing to show that it's a solid because it's showing massive movement lines here. And with a solid, we're only going to get vibration. We need an organized pattern. This is also, again, looking more like molecules, but formula units can't exist alone. They have to exist in a crystal with many, many other formula units. So star them if you got them right, and then we're going to take it one step further, okay? Take it further. We want you to practice drawing a particle diagram for an alloy, and we will do this as a warm-up after Thanksgiving to make sure that we're kind of all on the same page. But let me just go through this with you. In our penny alloy lab, we mixed copper and zinc to form brass. On your paper, I would like you to draw 3 boxes. Oh, of course it says as shown below. I forgot to draw them in here, but just 3 boxes right next to each other. 1, 2, 3 squares on your paper. In the first box, I want you to draw a particle diagram of copper. You can label the box on the outside as copper, but then go ahead and draw copper as a particle diagram, okay? So again, we're looking for things at the particle level. In the second box, draw a particle diagram for zinc. And in the third box, draw a particle diagram of brass. Okay? In order to do this correctly, you have to think of the definition of an alloy so that you understand what's happening with the zinc and the copper when we're making brass. Also, I would like you to draw a minimum of 16 atoms in each box and make sure that you're differentiating between atoms of different elements. That can be done with different colors or different shadings or whatever you need to do. But make sure that zinc and copper, make sure different elements do not look the same in your particle diagrams. All right, good luck, and then have that assignment ready to show on your way in the door at our next class. Thanks.